acids for us very important. If this formic acid, now what's the difference between this acid and other carboxylic acids? Here, as you see, as radical, you have directly H. It gives to these acids specific properties, and because of here you have electrodonating alkyl groups with carboxylic group. So this acid is more acidic than other carboxylic acid. So it's if you look at its Ka, its Ka much more bigger and larger than other carboxylic acids pKa. And as you know, the value of pKa shows you how strong is your acid. Yeah. Now, other members of these tables are very weak organic acids. Now, what about its carboxylic acid structure and physical properties such as their high point or their solubility? If you remember for our first semester material, I talked about this, that carboxylic acids can form hydrogen bonds, and really your carboxylic acids in form of dimers. When one carboxylic acid OH groups H atom forms hydrogen bond with second carbonylic acids carbonyl group. Now, hydrogen bonds also explain the water solubility of this compound. Of course, I'm discussing about carboxylic acid, so where your radical, this organic part is small. When we increase this organic part, so its solubility decreases and decreases. Why? Because of inorganic part is non-polar part, and the organic part, COH, is non-polar part of this molecule. So, with decreasing R, your solubility decreases. Now, what about carboxylic acids dissociation in water? As you, if you remember from your general chemistry course, for dissociation of acids, you always need water molecule. Why? Because of acids are covalent compounds and you haven't here ions as in the basis. Sodium hydroxide is ionic compound, so it can conduct electricity in molten state and in aqueous solution too. But when we discuss about dissociation of acids, in any case, you need, of course, water molecule here, which takes H proton from your acid molecule, and finally you get an ion and hydronium ion. So really, because of these carboxylic acids are weak acids, so they are weak electrolytes, and for all these acids, you can generally write the K equilibrium constants ratio, which looks like this equation. So anions concentration, equilibrium concentration, of course, multiply on hydronium ions equilibrium concentration, and simply you can write directly H1 plus. Here instead H3O with 1 plus, because in any case everyone knows that here you need water molecule for formation this H1 plus proton, for extraction H1 plus from your acid molecule. And of course your acidic H atom is H atom which is in this carboxyl group COOH. Nobody takes this H atom as acidic H atom, which determines the nature of organic acid, carboxylic acid. Now here you have, once again, K equilibrium is not very clear picture. I hope that you see here that 10 in minus 6 degree. What that means? It means that this acid is very weak acid. Now we discuss about the, yes, this one is the trial name of this acid is acetic acid, or this one is ethanoic acid. Do you remember the suffix of COOH group is oic acid. So ethanoic acid, because of here you have 2 carbon atoms. Now what about strength itself and source of carboxylic acid? If you increase number of electron withdrawing groups in radical, so in organic main part of your carboxylic acid. In this case, you increase the acidity of your carboxylic acid. For example, if we take acetic acid and its Ka equal to 10 in minus 6 degree, yeah? So then when we discuss about monochloroacetic acid or dichloroacetic acid or trichloroacetic acid, this one is very strong organic acid. Why? Because of here you have 3 electron withdrawing groups, and here you have inductive effect, so they attract these electrons which are in the bond with the carbon itself. This carbon attracts 2 electrons which are in this bond itself, so it means that oxygen which is bonded with H atom attracts these 2 electrons, and finally your H1 plus proton can be removed easily. What it means? It means that this acid is more strong than, for example, monosubstituted or disubstituted acetic acid. Now, if we compare strength of this acid, so it has equal strength like sulfuric acid. So it's very strong. And of course, if you change your halogen on more electronegative halogen, for example, fluorine, of course, with fluorine, this acidity increases too. Why? Because of fluorine's electronegativity higher than chlorine's electronegativity. Now, what about reactions itself, carboxylic acid? Of course, is other mineral or inorganic acids. They can act with metals, with hydroxides, with salts. Right now, here we have only neutralization reaction between carboxylic acid and sodium hydroxide. Finally, you get, as you see here, nitrogen, so you get salt and water molecule. So it's a normal neutralization reaction between weak carboxylic acid and a strong base. And as a product, you get sodium acetate or carbonate. If you want a general name of this compound, acetate if you have acetic acid as carboxylic acid. And as you see here, you get weak base, so conjugated base of this one. And water molecule, which pKa is 16. So because of here you get water molecule, your reaction really is reversible, and it always shifts to the right side. Now next reaction is methods of preparation of carboxylic acids. If you remember, we have discussed about aldehydes as sources of carboxylic acids. But if you take primary alcohol after oxidation with strong oxidizing agent, do you remember? If you use strong oxidizing agents such as Jonas reagent CrO3, so here you can't remove your aldehyde from your reaction mixture because of this aldehyde undergoes in oxidation, and finally you get this carboxylic acid. So from primary alcohols you can get aldehyde, and from aldehyde after oxidation you get finally your carboxylic acids. And remember that here you have the same number of carbon atoms and the same structure of your radicals. For example, if you take some primary alcohol which looks like this, CH3, CH2, CH2, OH, and after oxidation, and here once again, if you want direct preparation, your carboxylic acid, you have to use strong oxidizing agents such as CrO3. So here you get CH3, CH2, COH, first of all, aldehyde, and second step is oxidation of itself. Aldehyde, CH3, CH2, COOH. As you see here, you have the same number of carbon atoms and the same connectivity of atoms. So I haven't changed this part, this one. You only change this part. So aldehyde group, and then you get carboxylic acid. This is one method for preparation of your carboxylic acids. Now, what about acids which look like this? It's aromatic compounds. This one is total. Do you remember this? Aromatic ring, and where you have CH3 group. Now, it's very important reaction. Why? Because if your carbon, which is bonded with aromatic ring, has H atom, so after oxidation with potassium permanganate and heating, it converts into benzoic acid. And it does not matter how many carbons you have here with a benzene ring. For example, if you take something like this, CH2, CH2, CH3. After oxidation, in these conditions with potassium permanganate and heat, once again this part oxidized and gives once again benzoic acid, like this. But if you have something where you have not this H atom with carbon, which is directly connected with the benzene ring, in this case, your benzene ring oxidized. And it gives COOH group, such as, for example, if you have something like this. Look, C and CH3 three times. As you see, this carbon has an H atom. So in this case, after oxidation, you get this carboxylic acid. So benzene ring oxidized. If in benzene ring you have two methyl groups after oxidation, you can get dicarboxylic acid. Now look, like this. Two methyl groups, and after oxidation you get here dicarboxylic acid. So 2COOH group. So all these methods are methods for preparation of your carboxylic acids. Now the main problems which we have to resolve in this chapter is formation, is reactions of carboxylic acid derivatives. Now you have four classes of carboxylic acid derivatives. So compounds are these compounds. First one, ester. Second one is acyl halide. Halide because of its general name of halogen, so Cl or Br, it does not matter which one you have here. Acyl, not alkyl, acyl halide. Then acid anhydride and primary amide. Now let's start from our esterification reaction. Its formation ester from carboxylic acid and alcohol. Now, if you have, for example, acetic acid and some alcohol, which one you want? For example, if you have methanol. So, esterification reaction means that always group of carboxylic acid and H group from hydroxyl functional group of alcohols gives water molecule, and second organic product is always ester. Now look, take this one and this part goes here, and finally you get ester, CH3, COO, and then CH3 plus H2O. It's esterification reaction. And generally you can write this reaction like this, where you have R as radical here and here, and finally you get ester. So esters have a very pleasant smell, smells very pleasantly, and they have low boiling point, and after reaction with water you can directly get once again acid and alcohol. As you see, this reaction is a reversible reaction. So you have to remove your ester from your reaction mixture or water from your reaction mixture for shifting your equilibrium always to the right side. It's one way how you can get finally your alcohol. Now this reaction is hydrolysis of ester. So if you have ester and if you heat, for example, your ester in sodium hydroxide solution. So, in this case, sodium hydroxide acts as nucleophile, and this one separates this R, and instead R here you have Na, and once again you get alcohol. Now, it's very important in esters, remember that this part is your living fluid. So, in case of sodium hydroxide, so this Na goes here and H goes here. This is slightly different reaction. Really, in all cases, this is everything is your living fluid, to which H atom goes, for example, in reaction with amides or in reduction reaction. Now, here, in this case, this sodium goes here and this part goes here. So finally, you get salt of an acid and alcohol. Of course, you can carry out this reaction with water. But in case of water, you get, once again, reversible reaction. But if you use sodium hydroxide instead water molecule, so in this case, you get salt and reaction is irreversible. That's why better, if you want carry out the reaction of hydrolysis of esters, it's better use sodium hydroxide. Now, next reaction is reaction with ammonia. Now, if you have any ester and ammonia, the name of this reaction is aminolysis. Hydrolysis reaction with water and aminolysis reaction with NH3. Now, once again, I write some particular ester O C2H5, or something like this. Plus, now ammonia always write like this. In this way, you can easily write the product of your aminolysis reaction. Now, look, this part is your living group. H from ammonia always goes to this part, and this part goes instead your OC2H5. So, what will be the product of this reaction? CH3CO and H2 plus CH3, CH2, OH. Now, so after aminolysis of esters, you can get amide, it's second derivative of your carboxylic acids. This amide, not amide. So from esters, after reaction with ammonia, you get amide. Now, second one is reduction reaction. Now look carefully how I write this reduction reaction. This is very good. Here you have very good reducing agent. It's lithium, aluminium hydride. Now, why this group is very good? In this reaction, if you have here some double bond between carbon atoms, only this part takes place in reduction reaction, not your double bond. So you can get a product where once again you have your double bond. Now let's discuss about reduction reaction of this one. Look. CH3, C, double bond, O, O, CH2, CH3, really 4 H atoms. Yeah? Here you have 4 H atoms. Now look. 2 H atoms go here, 1 H atom goes here, and 1 here. So, from this part, you get CH3, CH2OH, plus second part is CH3, CH2OH. So, finally, you get 2 alcohols. Once again, after reduction of esters, you as a product, you get alcohol. Now, if in ester you have same number of carbon atoms in this part and in this part, so finally you get only 1 alcohol. As you see here, you get only ether. But for example, if you have something like this, CH3, CH2, C double bond, O, O, CH3. What about reduction of this one? In this part, you have 3 carbon atoms, yeah? So finally, from this part, you get, after reduction, alcohol, where you have 3 carbon atoms, so propanol, 1 propanol, or prop 1 O, CH3, CH2, CH2, O. From this part, you get methanol. CH3O. Once again, this is your living group. 1 H from these 4 H atoms goes here. 2 H atoms goes to this carbon and 1 to this carbon. Finally, you get CH3, CH2, CH2OH, and from this alcohol part, you get second molecule of methanol. Once again, yes.
1 H goes to all to the O here.
Yes, 2 H atoms goes to this carbon and 1 to this carbon. So finally you get this alcohol. So this is reduction of esters. As you see,
1 to O and 1 to C to the carbon and 1
two H atoms go to the carbon. So CH2. 1 goes to this oxygen. So finally you get 2 alcohols, 2 different alcohols. If you have same composition in this part and this part and in this part, of course here you get 2 molecules of 1 same alcohol. This is reduction reaction. And in this case, from this part you always get primary alcohol, always. Because this part converts into CH2OH+. Questions? Any questions here?
No.
No. Now, next reaction. It's once again formation of other class derivatives, carboxylic acid derivatives. It's acyl halides. Acyl halides. Where instead OH group, you have some halides. Now, here we are discussing about reactants which form these acyl halides. You have 3 types of these reactants. It's PCl5, PCl2, and SOCl2 or thionyl chloride. Now, here in all these reactions, you have same organic product, acyl halide, but you have different inorganic products. In this case, in this reaction, inorganic products are important. Now, if you have RCOOH, I write directly R because for all carboxylic acids, the reactions product, organic product is the same. You change only R in this case. So now look, plus PCl5. So here you get RCOCl plus POCl3 plus HCl. So in case of PCl5, you get this and this as inorganic Now, second one, RCOOH plus PCl3. Here you get RCOCl plus H3PO3 or postpolar basic. And third one is reaction with thionyl chloride. These reactants we use for formation alkyl halides too, if you remember, from alcohols. We can get this product alkyl halides, and once again we choose which reactant we have to use. And this depends on the product's boiling point. Because of our aim, separate our acyl halide or alkyl halide from reaction mixture. Yeah. Now, if you have RCOOH plus SOCl2, so here you get RCOCl plus SO2 plus HCl. Now, in this version, as you see, you get two gaseous products in last reaction. And this fact we can use for shifting our reaction to the right side. And of course, this one is the best as reactant. Why? Because of here you have a reversible reaction and your reaction always shifts to the right side. Now, yes, I show you this reaction. So, what about itself reactions of acyl halides and why they are so important? Yes.
This HCl.
Yes. G. Gas. Gaseous. So these two compounds are in gaseous state. So they can remove flow from reaction mixture. That's why the formation of this gaseous product always shifts the reaction to the right side. Now, why acyl halides are so important for us? Because of here you have very reactive part Cl in this reaction, and it's from these acyl halides you can form some compounds. So first example is a reaction with water. So, if you have RCOCl, this is your living group. Cl is your living group. Stop talking or go out. Now look, HOH, first one. It's hydrolysis or reaction with water molecule. Cl is your living group. H always goes to your Cl. So you get R, C, double bond, O, OH plus HCl. What do you get here? What is this?
This is carboxylic acid.
Yes. So acid halide after hydrolysis gives carboxylic acid. Esters after hydrolysis once again gives carboxylic acid and water. Alcohol. Now, if you have once again acyl halide plus some alcohol, and please always write these two compounds face by face with their functional groups. When these functional groups look at each other, in this case, easier write your reaction. So once again, Cl is your living group. H, what will be the product? Yes, ester. Ester and HCl. So RCOOCH3 plus HCl. Now, here you have some reactions of this one. Now, reactions of acyl halides with ammonia. With ammonia. Now, here we use 2 molecules of NH3 and 1. We use here NH3 because of here formation of HCl is not very good for this amine because it can react with HCl and give some salt. So, with using 2 molecules of ammonia, here your HCl converts into ammonium chloride, which can't react with this acetamide, and finally you can remove from your reaction mixture your product or amide. Now look, you have R, C, double bond, O, Cl. Once again, this is your living group. Plus 2 molecules of NH3. Now, when we discuss about 2 molecules of NH3, look, itself, ammonia is amphoteric compound, so it can react with itself, and it gives NH4 with 1 plus ammonium cation and NH2 with 1 minus amide. So 2 molecules of NH3 gives NH4 1 plus and NH2 1 minus. So this NH4 takes this Cl, which is cleaning group. That's why your inorganic product is ammonium chloride, and NH2 group you have instead Cl. So finally, with 2 molecules of NH3, finally you get amide RCONH2 and ammonium chloride. Of course, here you have plus and minus because of this one is ionic compound. So now this is amide. Once again, this is primary amide. Because of nitrogen has 2 H atoms, and this part is radical. If you want reaction of acyl halide with, for example, primary amine. Now let's discuss about this reaction. Primary amine. Look, you have acyl halide, and once again, it does not matter which radical we have here. We need only this part. We'll need only this part. Plus, look, H2NR. What is this? Amine. Primary amine. Yeah? Because of nitrogen has only 1 radical. And it's connected it's bonded with 2 H atoms. Now I write this H atom separately, like this. Which one is your living group here? Cl, yeah? This Cl takes this H atom, and finally you get RCONH R plus HCl. As you see here, you get secondary amide. Now, once again, if you use ammonia, you get primary amide from acyl halide. If you use primary amine, you get secondary amide in your reaction. If you use secondary amine, so finally you get tertiary amine, where your nitrogen has 2 radicals. Here you have 2 radicals, only 1 radical here, and this part we can discuss as second radical, so secondary amine. Questions?
Primary, we get secondary. Primary gives secondary.
Primary amine gives secondary amide. Secondary amide gives secondary, tertiary amide. Yeah. Now what about this one? What is this? It's carboxylic acids anhydride. Now how you can get carboxylic acids anhydride? If you have monocarboxylic acid, for example, if I take 2 molecules of acetic acid, CH3COOH, and second one, CH3COOH. After removing or dehydration, you get from these molecules acetic acids anhydride, which looks like this. Or another version you can write like this, student. This is anhydride. Now, if you take different monocarboxylic acids molecules, so in this case, you get mixed anhydride, where you have different radicals in these 2 parts. Here you have same radicals. Why? Because of I have taken the same molecule of carboxylic acid. Here you have acetic acids. You get acetic acids anhydride. Now look, which reactions are typical for these compounds. First reaction is hydrolysis of this one. Of course, here you need conditions, some conditions. For example, when we discuss about reduction, here we need aluminum chloride or lithium aluminum chloride. When we discuss about esterification, here reaction mechanism needs always acid as catalyst, and your alcohol acts as nucleophile, and your carboxylic acid part acts as electrophile. So you have in this chapter all these mechanisms, and we discuss about this mechanism, of course, in class too, where we will have enough time for this. Now let's only discuss how you can write the products of this reaction. So you have this one. This is your leaving group. This part is your leaving group. So, plus, okay, HOH, so hydrolysis. H goes to leaving group's oxygen. Other part goes to your leaving group's carbon. So finally, you're going to get 2 molecules of acetic acid, yeah? So here you get CH3COOH plus CH3COOH. This is your one reaction. Now, if you have a reaction with alcohol, once again, I write here, alcohol like this, HO. And for example, if you have here CH3, once again, H goes to your leaving group. This part goes to your leaving group's carbon. What will be the product of this reaction? So, class. Yes, ester, and once again carboxylic acid. So, as carboxylic acid, here you have acetic acid, CH3COOH, and second product is ester, CH3COOCH3. Now, if you have ammonia, try it once again because of my we can hear a lot of arrows. So yes, it's not clear right now. It's the product and what is your reactant and so on and so on. Okay. Now look, you have in the middle oxygen. Once again, it's our aldehyde, sorry, anhydride plus. Once again, write H and NH2. NH2. And your H goes to your leaving group's oxygen. So H goes here, and this part goes to this carbon. So what will be the product? Amide. Yes. Primary amide. And once again, carboxylase. CH3COOH plus CH3CO and H2. So you get carboxylic acid and amide. So as you see, all these carboxylic acid derivatives itself are very reactive, and they can form different molecules, and they convert into each other, and it's very good. Now, here you have reaction of itself carboxylic acid with ammonia and formation of amide as product in this reaction. Right now, I will discuss about compounds which, about dicarboxylic acids, which can form cyclic anhydrides. Cyclic anhydride. Now, look, if you have something like this, CH2, 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 CH2. And here you have COOH, COOH. So, by removing water molecule, so you get here cyclic anhydride. CH2, 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 and here you have C double bond O, and wait. In the middle, you have oxygen. This is your cyclic anhydride. Okay. Yes, that's all. Finally, in this